Hi, welcome to the second session on the series What is Complex Analysis About? In the last session, the first session, we said that a holomorphic function, that is a function which is differentiable on an open set in C, is analytic. That means it's locally a power series. That is, given any point A in the domain, open set, then f of z is of the form summation Cn z minus a to the power n, where Cn will depend upon a, and this is for all z, so that z belongs to bar, where bar is contained in u. Okay, so locally it's a power series. That's what we mean by analytic function, right? And once it's an analytic function, we saw that any power series is always a primitive. What does it mean? There is another power series g of z, so that g dash z is the given power series f of z. So naturally, if I have a function which is holomorphic f from an open set in C to C, then there should be primitives locally, because f is locally a power series, therefore locally there should be a primitive. That means there exists a function g which is holomorphic on u, perhaps not necessarily on u, but locally in an open disk bar, so that g of z, g dash equal to f. Okay, so this is our guess. We kind of arrived at this result based on the fact any holomorphic function is locally analytic, that is locally a power series. Now, how to prove the existence of such a thing? That is what Cauchy's theorem deals with. As I said, the entire Cauchy theory depends on two facts. One is any holomorphic function is analytic, and second, any holomorphic function has local primitives. It's okay. How to prove the existence of local primitives? Okay, that's what we are going to deal with today. Okay, again, as I said, this is expository, and even for those who have gone through a course, it may be a little overwhelming. And if you are yet to learn a course in complex analysis, certainly it will be tough. But please listen to it. Try to understand as much as possible. Even 20-30% is good enough. When you learn the subject, it will make more sense why you are proving results, because usually courses keep on proving things. You don't know what is the aim, what we are aiming at, why we want to do certain things. Nothing is clear. Alright, the only thing at best what you know is there is a theorem, there is a rigorous proof, I learn it. Okay, this will break that circle. Okay, stay tuned. Yeah, right. Let us, yeah. Okay, this is what we have. So let us do that. So first let us recall something what we know about in real analysis. If f is a function, okay, let me just choose a small one, from an interval j in R to R, j an interval. Okay, maybe close, open, finite, and unbounded, I don't care. Okay, and assume this is continuous. Okay, then there exists a primitive of f. Name that is what is given by fundamental theorem of calculus. What does it say? Define g of x, fix a point C in J, and define g of x to be C2x f of t dt. Then g is differentiable, and g dash is f on g. Okay, this is the first fundamental theorem of calculus. All of you must have learned it in your real analysis course. Alright, so this is surprising result. You see that I don't have to assume f is differentiable. The moment f is continuous, I have a primitive. Okay, very good. So this is the motivation. So let us go back now. Suppose f is from U open set in C to C holomorphic, right? I want to show whether there exists, and suppose A is in U and let R be positive so that BAR is contained in U. Question is, does there exist a G from U to C, sorry, BAR to C holomorphic and such that G dash equal to F? That is locally primitive exists. That's a question. So what we want to do is, let us look at BAR. This is my U and this may be my BAR. Okay, it may be even bigger, I don't care. This is my A. Alright, now notice that BAR is convex. What does it mean? Okay, any line segment, okay, take any 2 points Z and W in BAR, the line segment ZW, this is my notation, Z plus 1 minus T times W 0 less than or equal to T less than or equal to 1. Okay, it starts from Z to A. In particular, the line segment for every Z in BAR, the line segment AZ, which is A plus T times Z minus A, okay, lies in BAR. Right. So now you notice that I have a function defined from 0 1 to C. How do I go? From 0 1 I go to first U, and from U I go to C via F. What is this function? T going to, look at T times Z minus A, okay, Z minus A, and that goes to F, sorry, that goes to F of A plus T Z minus A. Right? More generally, so you call this, let us look at gamma T equal to, this is T varies over 0 1. Now this is contained in this. Okay. So more generally, let gamma be a path from 0 1 to U so that gamma prime T is defined. That is, you write gamma T as U of T plus I times V of T, then gamma prime T is U dash T plus I times V dash T. Okay, and I assume this is gamma, this is continuously differentiable. That means gamma prime is continuous. Right? Then I can define the so-called path integral for any continuous function, and suppose f from U to C is any continuous function, not necessarily holomorphic, then I can define integral of f over gamma to be integral of 0 to 1 f of gamma t gamma prime t dt. Notice that this is continuous, this is also continuous, therefore this integrand is continuous, therefore the integral exists. This is called path integral of f. Sometime the older notation is contour integral of f along the path gamma. Right? Okay. So now you see that if I define g of z to be, okay, let me write the path, simply write a of z, the path, okay, this denotes the path going to a plus t times z minus a as 0 less than or equal to t less than or equal to 1. Let me write this as a path az of, okay, and if you want call it path gamma z, therefore f of gamma z of t gamma z prime of t dt, if you want 0 to 1, or I will simply denote this by f over gamma z. Okay, this is the shorthand notation. This is a shorthand notation. And its meaning is this. This is the meaning. Okay, what does the symbol stand for? It stands for this object, right? So in view of fundamental theorem of calculus, I may be tempted to ask the following question: is G differentiable on BAR? Do you see why G is defined only on BAR? Why it is defined only on GAR? Because I have to look at only Z which are in the thing. Then only the line segment makes sense, right? Therefore the path integral makes sense. You understand? So answer is yes. Okay, and not only that, G dash is above Z on BAR. Okay, so what do you think I have proved? I have shown that given any holomorphic function, I define what is meant by a path integral along a path. What is the path we are taking? We are taking the simplest path. Since open disk is convex set, I am taking only the line segment connecting A to Z. Okay, then I integrate the function f along the path. Okay, then I get a function. As you did in fundamental theorem of calculus, the same kind of estimate will give you G is differentiable at each and every Z, and G prime Z is nothing other than f of Z. Okay, so what do you think I have proved? We have proved that is any holomorphic function admits a local primitive. But there is a subtlety here. You may be tempted to think these are the subtleties which is never explained. Even this existence of primitives is never explained. You will see in my book it's explained. To prove this, we actually needed a subtle point. We needed the fact f is holomorphic. Okay. Unlike in the real case where I just needed f to be continuous function. Okay. This is only for Z along that. Okay. On all of you, if I want to prove this on all of you. Okay, we'll come to that later. Okay. Alright. The next thing. Okay. So we have proved meaning. Okay, so now we have found a fact. What is the fact? Any holomorphic function f from U to C has a admits local primitives. Okay, good. That's clear. All right. Now the next thing comes. If you let's have a digression. I do not know whether you will learn line integrals in your in 2 variable or 3 variable calculus. Okay, there suppose assume U is an R2 open, and capital F is a function from U to R2, okay, which is, let us say, continuous. Then you call it F is a vector field. Okay, because f of xy will be f1 of xy or u of, let us say, u of xy and v of xy, because these are two real numbers and therefore u is a function of two variable but real valued. Similarly, v is a real valued function of two variables, so you can write it, right? Then you say f is a conservative vector field if there exists a function f from u to r which is c1 that is continuously differentiable, so that the gradient of f, which is del f by del x, del f by del y, is f of xy, is f. Therefore, u of xy is del f by del x, v of xy is del f by del y. Okay. See, unfortunately, these kind of things are never learned by students. So, what you there you say that if f is a conservative vector field, and if gamma is a path in u, then integral of f over gamma, okay, any vector field, okay, you define to be integral of the same way f of gamma t, this is dot product with gamma prime t dt, where if gamma may be from 0 1 to r2. Okay, you see that this is exactly the same way you define the path integral for a complex valued function. Okay, now if f is a conservative, this is a fact. What is the fact? If f is a conservative vector field, okay, intuitively it means f admits a primitive. What is a primitive? That is a little f. We saw that this is a little f. I can think of this as a primitive. It may not be called that way. They will usually call it a potential function. They will call it a potential, but let's not worry about. Okay, if this is a little f is a primitive of capital F, then integral of f over gamma is nothing other than little f of gamma at 1 minus f of gamma at 0. That means this depends not on gamma but only at the end point. The line integral of the vector field f, a conservative vector field, on a path gamma depends only on endpoints. In particular, okay, pause, review, proceed. In particular, assume gamma is closed. That means the endpoints are the same. Then what is our integral f over gamma for conservative vector field? This must be 0 because this is f of gamma 1 minus f of gamma 0, but gamma 1 and gamma 0 are the same. Therefore, f, the value of f is a function. Therefore, this is 0. Okay. So please recall, review in case you have not learned. It doesn't matter. It's not necessary you have to remember that, but just go through this because this will help you to understand what I am going to say next. So let us put a PRP. Okay. Now come back to complex analysis. Suppose f from u to c is holomorphic, right? Then I know F admits local primitive. Right. Suppose therefore let gamma be a path so that gamma of t lies in some of BAR which is completely contained in U. Okay, in fact whatever I'm going to say it would be enough for any convex set, but that's not, let's not worry about such things. Okay, right. Then what we want to claim is, since then on BAR F has a local primitive, has a primitive, say G, that is G is a function from BAR to C holomorphic and G dash equal to F on BAR. Therefore what should I expect? Therefore integral of G over gamma is nothing other than, sorry, integral of F over gamma is G of gamma of 1 minus G of gamma of 0. Notice that this is a complex number, that complex number is nothing other than that. So in important corollary, if gamma is closed path lying in BAR, then integral of F over gamma is 0. Okay, right? Gamma 1 equal to gamma 0, therefore it must be 0. So this is the Cauchy's theorem, the simplest version of Cauchy's theorem. So what does it say? Let F from U to C be holomorphic let gamma be a path. Remember my path are assuming 0 1 to U, which is C1, continuously differential path. Okay, in U such that gamma of t lies in BAR for all t in 0 1. Okay, assume further gamma is closed. Maybe let us say be a closed path and gamma of 1 equal to gamma of 0. Then the path integral of F over gamma is always 0. This is Cauchy's theorem. Do you see that why it's very natural? Yeah. So whatever I have said so far, let me hope I will remember to come back and do the screen sharing properly. In the last lecture I forgot anyway. So now do you see what the Cauchy theorem is very natural. So what I have proved? I have proved a very restricted version, but whatever I said can be done for any convex open set or even the so-called star-shaped open set. So let's not worry about those things. So if F is holomorphic on a convex set or an open disk, then it admits a primitive on that open disk, and hence integral of F over gamma for any closed path in that open disk will be 0. This is Cauchy's theorem. Okay, whatever be the closed path, as long as the path is contained in open disk, later we will see it, any convex set will do. Okay, this is the Cauchy's theorem. Now you see that how Cauchy's theorem comes out. Okay, now let me take few more minutes and try to say something what I can derive out of this. Remember what we said, the culmination of Cauchy's theory is the any holomorphic function is analytic, right? Which, and hence it will be infinitely differential, will be very easy because locally a power series. On the way we saw that if it is true, then every holomorphic function admits a local primitive. Now I want to know how to prove that local primitive exists. This, okay, we showed how to prove existence of local primitives, okay, on any open disk on which the function is holomorphic, right? And using that, we said just because of that we derived the Cauchy formula, Cauchy's theorem, namely any holomorphic function on an open disk, okay, and if gamma is any closed path in that open disk, the path integral of f over gamma is 0. Yeah, okay. But how am I going to get what I said earlier? I said any holomorphic function is locally a power series, it's analytic. How does this help? That's what we are going to deal with in the second part. So let's go back to, okay, there is a slight extension of Cauchy's theorem. It says that suppose f from u to c is continuous and holomorphic on the open set u minus some point a, where a is a point in u. Okay, then for any path gamma in u which lies in an open disk, B, not necessarily with R, it may be anything, B, P, R containing U, integral of f over gamma is 0. This is a slight extension. This is a very easy extension once you have proved Cauchy theorem. You see that? What does it say? It says that if f is continuous on all of U, but holomorphic except at one point, and then integral of f over gamma is 0. Now I am going to say something which may not make sense if you have not learned complex analysis earlier. I am sure all of you must have learned about singularity and Reimann theorem of removable singularity. What does it say? It says that if f is holomorphic on an open set except at a point, and if it is bounded on the open set or it's continuous on that open set, then A is a removable singularity, and hence f is holomorphic on all of u. Do you recall that? When your teacher proved that, he may not have come back, he may not have revisited this theorem. If Reimann's theorem is true, then you see that this is obvious result. I should expect the extension of Cauchy's theorem. You see that this kind of going back and forth is the one which makes you get mastery over the subject. It may be a little confusing, but try to understand. Okay, I have gone through, then I went to singularity, I learned about Reimann's theorem of removable singularity. What did it say? If f is continuous on all of this open set and holomorphic except one point, then it's actually holomorphic on the entire open set. If that be the case, and if gamma is any closed path, I said it should be closed path, I forgot to write here. Okay, and so that it is contained in some convex set or an open disk, then the line integral of f over gamma is 0. This is precisely what your ordinary Cauchy theorem said. Do you see that? Think, pause, review. Okay, pause, review, proceed. Okay, for those who have learned, okay, recall Reimann's theorem on removable singularity. Okay, now okay, assume that now what does it help? Okay, now is the thing, suppose F from U to R, U to C is holomorphic, right? Fix a point A in U, fix an R positive so that BAR is contained in U, and so this is my thing. Okay, this is my open thing. Okay, now let's choose a point A and choose any R. Okay, this is R and this is capital R. Okay, so let us go back. Let 0 less than or less than capital R. Then the path gamma t, which is okay circle. What is the circle? The circle is going to be this: A plus R e power it. What is e power it? Cos t plus I sin t. And if you want, you can put a 2 pi. If therefore 0 less than or equal to t less than or equal to 1. So this is the path. Okay. Therefore this path gamma t completely lies in BAR and hence is completely contained in BA capital R. Right. Now let's look at the function g of z, which is f of z minus f of a by z minus a for z not equal to a, and f dash of z a. Right. What do I know about g? Remember, f of a is a constant and z minus a is a constant. Where z is, let us also make sure where is z. Z is in BAR. It's in the open disk. Okay, right. Now let's look at this function. Okay, this function is g is holomorphic on BAR minus a singleton and continuous on BAR. Therefore, what do I know? Therefore, integral of f or integral of g over gamma was 0. Right? But what is integral of g? Integral of g is over gamma is f of z minus f of a by z minus a. This is the function g. But this you can think this is the circle f of z by z minus a over the circle gamma equal to integral of f a by z minus a over the circle. This you can compute it to be 2 pi I, let me say f of a into integral of 1 by z minus a over the circle gamma. This you can compute it to be 2 pi I. Okay, so you got what is called the Cauchy integral formula. Okay, with the stated assumption as above. For all z in BAR, okay, we have f of a is going to be 1 by 2 pi I f of z by z minus a over the path gamma. So in particular for every z you just have to do that. So from the extended version of Cauchy's theorem we arrived at a Cauchy integral formula. Now Cauchy integral formula is the one which is going to give prove the fact my function f is locally analytic, because 1 by z minus a, alright, f of z by z minus a, okay, that I can use the geometric series expansion for 1 by z minus a, alright, and that is uniformly convergent within the domain. Therefore the integral over the sum can be taken as sum over the integral. So you would have got power series. I will explain it in the next lecture. But go through this. If you had understood this, after that, we can, in a regular course which I am going to give, I will prove all these things rigorously. Don't worry about it. So this is the culmination. In fact, for all properties of holomorphic function, even holomorphic functions with the isolated singularities, etc., the Cauchy integral formula is the crux of the matter. Whatever you want to talk about, like be it maximum modulus principle, this or that, everything you can prove using by Cauchy integral formula. Okay, see, for any holomorphic function, okay, any property of holomorphic function is again, the word may be little abstract sounding, but listen to it. Any property of holomorphic function is a global avatar, global manifestation of the property of a power series. For example, if you have gone through complex analysis course, you would have learned maximum modulus principle, minimum modulus principle, open mapping theorem, okay, and mean value property, various kinds of stuff. Okay, all those things come about from here. Okay, just before I end up my lecture, there's one more thing which I would like to talk about and stop there. So is this something very, okay, look at this Cauchy integral formula. Okay, is this natural? That means to be expected? I am saying yes. Why? Remember, my f, you to see holomorphic, that means it's locally a power series. Therefore f of z is, and suppose for every a in u, f of z is going to be cn z minus a to the power n equal to 0 to infinity, right? Okay, and we also know what is cn's are, the derivative of nth derivative of a at n factorial, but that's not needed for us, right? Okay, now this is uniformly convergent. Let us look at BAR, and Z is in BAR, uniformly convergent on BAR for any R less than capital R. Okay, therefore if I take R 0 less than R less than R and 0 less than R less than R1 less than R, etc. So let us look at, okay, suppose I integrate f over a circle gamma where gamma of t is a plus r1 e power I 2 pi I t 0 less than or equal to t less than or equal to 1. Okay, and this is uniformly convergent. Therefore I can think of this, let us look R, think of this is going to be, okay, integral of summation cn z minus a to the power n 0 to infinity, this is over gar, but because uniform convergence I can integrate this cn z minus a to the power n over gamma. But notice that, okay, so therefore integral f, so let me say f of this by z minus a. Therefore let me do it. Therefore integral of f of z by z minus a over gamma is going to be integral cn over gamma cn integral z minus a to the power n minus 1 over gamma. You follow that? Yeah. But this, what is cn? This cn is nth derivative of f at a by n factorial, and this is over gamma. Remember, when n is greater than or equal to 2, z minus a to the power 1 has a primitive, namely z minus a to the power n by n, right? Therefore, for n greater than or equal to 2, this is 0. N equal to 1. Yeah, because that's a constant, that has a primitive. Do you follow that? So for n greater than or equal to 1, z minus a to the power n minus 1 has a primitive, namely z minus a to the power n by n. Okay, therefore all these things will be 0. Therefore the only thing which survives is but each one of them is 0. Therefore what do you think I get? What is f0 of 0? It is f of a by 0 factorial is 1, and therefore this integral of 1 by z minus a over gamma, this is your 2 pi I. From the definition of path integral we will get it. Therefore this is to be expected. So what I have shown is, okay, Cauchy integral formula is something we should expect. Okay, none of them is mysterious. You see that all these things flow from one single idea. What is the single idea? Any holomorphic function is locally a power series. It's an analytic function. From that, all the Cauchy related results, okay, you can guess why it should happen. In fact, you should see how to prove it now rigorously. Okay, so I have done all these things now. Then next important thing, the next session, what I am going to talk about is what is multivalued function, so called. Okay, many of you are mystified and always some kind of in a confused state. Logarithm, multivalued, a lot of branches of logarithm, various things. We are going to take it head on in the next session. Okay, a very small thing. Okay, in the fourth one I may talk about singularities. So that will be the end of this bird's eye view of complex analysis. Okay, I hope you will enjoy it, and please revisit all these things once or twice, especially with your friends. If your friends, you can discuss. No, he said I didn't understand, how is it related to what I learned, etc. You will discuss. Yeah, please do that. We will meet again.